Okay, so this is part 2 of Anatomy Intense Review. So one quick note from last class, going back to one of the systems that we already covered, and then we will do essentially the other half the systems. We have a little more than half the systems left, so I'm going to try to make them as brief as I can without losing anything. One thing I did lose on nervous system, and you can go back to nervous system to write this. I wrote it on muscular system, which is not where it makes sense. I just did that so I wouldn't forget to mention. Multiple sclerosis is one of the things for the nervous system that you need to be familiar with. And we actually covered this in 2 very different places, which is Anatomy 1, where we talked about kind of what autoimmune is and how we can distinguish between these different types of things. And then we also talked about it in Anatomy 2 along with the nervous system. So multiple sclerosis is autoimmune. That would be one important thing to know about it. An autoimmune disease, as a review, is where the immune system, for whatever reason, thinks that a healthy tissue is an unhealthy tissue. So it thinks that something that is part of us is a pathogen instead of being part of us, and it attacks whatever that is, basically wearing it down more and more and more over time. So it's autoimmune, and as with most autoimmune diseases, it is progressive, meaning it will worsen and worsen and worsen as time goes on. Most autoimmune diseases are progressive. In fact, I think you could almost safely say they all are. And a lot of them also have remission and relapse properties. They don't really ask about this on the test relapse. There we go. They don't really ask about remission and a relapse. This is just for your context so that you can remember what you need to remember about it. So remission and relapse kind of means that there might be points in time where your immune system is really targeting the tissue, and then other points in time where it's not targeting it quite so hard, and you have a slower progression during 1 year of time than you do during another year of time. So autoimmune is one of the things that you need to know. Anytime that you're answering a question about an autoimmune disease, the question that they're going to ask is what tissue is being attacked. So essentially with an autoimmune disease, you always have tissue being attacked by the nervous system. So anything that is autoimmune involves not nervous system, my goodness, immune system, sorry. So the immune system is attacking healthy tissue no matter what autoimmune we're talking about. So the question that they usually ask is, what tissue is it that's being attacked? So in the case of multiple sclerosis, if you're still writing what I have here, you might want to pause because I'm about to erase that last thing that I just wrote. So if we're talking about multiple sclerosis, it is nervous tissue. That's kind of the broad answer. So to just be able to say, oh, multiple sclerosis is where nervous tissue is being attacked is a really general, not so detailed answer. If they gave you the answer that is better, that is more detailed, you would be able to specify that it is the myelin sheaths that are present on certain nervous cells. So that is the specific thing that's being attacked. Multiple sclerosis is the immune system attacking myelin sheaths slowly over time, causing really big disruptions to really important neural signals. They can have the answer be this, and they can have the answer be this. So they could say multiple sclerosis is characterized by the immune system attacking, and the blank that you fill in could wind up being nervous tissue, or it could wind up being myelin sheaths. That just depends on what the answers are. So if you see that their answers are the 4 big tissue types, which that is one way that this question looks, where your choices are connective, nervous, muscle, epithelial. Those are just your 4 big tissue types. Needless to say, in this case, we can't pick myelin. We just have to identify that it is nervous tissue. If they were more specific, they might say myelin sheaths, axons, brain tissue. So they might specify some things, in which case myelin is very specifically what you're looking for. So add that to nervous system. Make sure you remember that from the nervous system. Another example of an autoimmune that was discussed in Anatomy 1 was rheumatoid arthritis, which is where the immune system is attacking connective tissue More specifically, it's attacking the cartilage that is in the joints. And so that's kind of what you're always up against if they're asking about an autoimmune disease. You know it's the immune system attacking healthy tissue. You know that's caused by an error that's making healthy tissue seem like it's unhealthy tissue. But you will have to specify, generally speaking, what tissue type is it? Is it epithelial that's being attacked, connective, nervous, or muscular? Or you may have to say it's this very specific teeny tiny thing that's being attacked, which also happens to be, of course, a certain type of tissue. So if you say that nervous tissue is being attacked, you're accurate. But if you have the option to say that myelin is being attacked, that is much more specific, therefore much more correct. So it depends on your choices. The next system is endocrine. And just like with the original stuff that we did in Anatomy 2 with endocrine, there is no way for me to walk through all of this. And if I did, it would not help you. So especially with endocrine, and I emphasize this everywhere. Everywhere in anatomy, I emphasize your thought process, because I cannot possibly tell you every little thing you need to know. And if I could, because I can get close, I can tell you almost everything you should know. But then you're trying to keep all that memorized and you're not able to really connect the dots. So you're not able to use the info. So what's more important than anything is your thought process and or your study process. So how you're thinking about the endocrine system will absolutely make or break your success with these questions. People who are good at following along with the endocrine system and carrying out the thought process that makes sense for endocrine questions do very well. People who second guess themselves on that and they try to just memorize the hormones instead have a very hard time. So there's one very easy way to do very well on your endocrine questions, whatever questions you get. That way, that thought process or study process involves knowing a few things, and they're all things that with just a teeny bit of background information that you do have memorized, you can figure out the rest of it on the spot. And that's what's crucial, because there's so many ways that they can rearrange these questions. So what is the thought or study process that you should be using? Hopefully you really took to heart what I said in Anatomy 2 and really worked on the thought process, because I described it there as well. In this packet, I'm going ahead a few pages to where you see some typed notes about endocrine. I think I went up about 4 pages. I actually do tell you right here in writing, here's what you're supposed to know for each thing in the endocrine system that you're supposed to have knowledge of. So the endocrine system, as a quick review of its general function, is one of the 2 systems that controls the entire body. So the 2 systems that they might refer to as control systems in the body are nervous and endocrine. So we already talked about nervous, and we talked about why the nervous system would be considered a control system. The other system that controls the entire body is endocrine. So endocrine controls the entire body in a very different way from how nervous controls the body. Endocrine controls it because it controls all of the chemical reactions, all of the metabolism functions that are happening throughout the body. So the endocrine system is responsible for making, releasing, transporting, and interacting with hormones. So hormones are chemical messengers that are important in all these different chemical reactions that your body needs. So the endocrine system is widespread. It's all over the body, and they're made up of glands. So when you think of endocrine system, you should always think of glands. So glands make and then release hormones. Each gland has its own hormones that it makes and releases. Some glands have just one hormone that they focus on. There's other glands that have 20 different hormones, maybe not quite that many, but there's definitely some that have at least 10, and they're all coming out of the same gland. So you can really start with glands, and you can think about each gland, which I gave you several pages here. I'm now backing up. I'll be going back and forth throughout this whole kind of time. So I gave you a couple of diagrams that are blank, and I did my best to leave you a lot of room to write. And I left you a couple of different ones with kind of the labels placed in different places, so that based on how you do your handwriting, hopefully you can find a good place to make your notes however they help you. And then I put one in here at the beginning that does have the hormones listed. It does not have the functions listed. What I discovered in Anatomy 2 with the way I had those notes written originally is it's so much information packed into this tiny little picture that it's not really effective. So I left it to you to have different diagrams that you can do different things with. This one will help you remember which glands you need to know, because I only labeled the glands that you need to know. They're in boxes, so you can't miss them. These are the glands that you need to know. There's not that many of them that you have to know gland-wise. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 11 glands that you need to be familiar with. Each gland, you need to know which hormones does it release. So in some cases, there's just going to be one, like the testes just release testosterone. In other cases, there might be several. Pituitary releases more than what I have listed here. But again, I'm only telling you the things you actually need to know. So these are the 4 that are critical to your knowledge for this specifically. Later on in nursing school, certainly you might need to know more. So essentially you want to start with where and what are the glands? Can you name the glands that you're supposed to know? And can you, very generally speaking, say where they are? So what they release, and whatever they release is also what they make, because they make it and then release it. So what they make and release, where they are generally. So there's no such thing, if you've seen the test before, you know that they don't put like a diagram and ask you to point at something like we did here. They just ask you like a general location. So knowing that the pituitary, hypothalamus, and pineal gland are in the brain is all that you have to be able to do. Knowing that the thyroid and parathyroid are in the chest together, that's all you have to know there. So just what they are and where they are first. You need to be able to list the hormones that are coming out of each of these glands at some point. So if I say pancreas, you need to be able to say insulin, glucagon. There is other things that the pancreas releases. So in this particular instance, you just have to trust me that I've got everything that's critical here, and you don't have to worry about it if it's not here. So if I don't have, somatostatin is the one that you might be familiar with for the pancreas, it's because I've never seen a question about somatostatin. So it's going to take up brain space and it's not necessary. So when I say pancreas, if you can say insulin and glucagon, you're well on your way. Of course, you also need to be able to say what insulin does and what glucagon does. But I would recommend starting with just the map, just knowing what 11 glands you're supposed to be familiar with, what they release, where they're located. Once you're good at all that, once you can kind of map it and sort of see this image in your head, then you can start to get into the real stuff, which is what is the function of the hormone? And based on the function of the hormone, so how does each of these hormones function? What is it for? And then that will allow you to say, where does it go? And the where does it go part is release site or manufacture site. This is the same thing I told you in the other class. So where is it manufactured, as in what gland does it originate in? That's based on how these are listed. So T3 is manufactured in the thyroid, so is T4, so is calcitonin. Epinephrine and norepinephrine are made in the adrenal glands. So the release site you already have checked off from here. What you're now going to do once you know where is the gland, what does it release, then you can start to say, what is the function of that hormone? So what is the function of insulin? When you think about what the function of insulin is, that should also tell you where insulin would need to go in the body. So with the endocrine system, part of the definition of endocrine glands is that they release hormone into the bloodstream. So essentially, to my knowledge, and especially in terms of what you need to know for this test, there's not really a situation where a hormone acts where it's released. So basically, every hormone that is released by the endocrine system enters the bloodstream. You know that what the bloodstream is there for is transport. So the whole function of the bloodstream, there's only one function for the bloodstream, and that is to take things from one place to the other. So your red blood cells grab the hormone, you have binding proteins that grab the hormone, and they take it wherever it is that it needs to go to engage in the chemical reaction it needs to engage in. That's always going to be true for endocrine. So you can always assume if something is released at the kidney, that's not where it does its chemical reaction. It's going to travel somewhere else. If it's released at the pancreas, you can assume the pancreas is not the action site. The action site is going to be somewhere else. So you know that they always travel in the bloodstream. That's some of what they ask. So they will ask what should seem, once you're done with all this, like a very simple question of what does an endocrine gland do? Or what happens when a hormone gets released? Or what is the connection between the endocrine system and the cardiovascular system? Because obviously cardiovascular is there to help the endocrine system get its hormones out there wherever they need to go. So those would be very simple questions. That's just how does the endocrine system work and what other systems and what other mechanisms are involved in making sure that it can do what it needs to do. What it needs to do being make a hormone, release it into the bloodstream, have it travel to a certain place, and in that certain place, once it arrives, it can engage in a chemical reaction, which was the whole point of making the hormone in the first place. So going back to the written part, which is a few pages up, here's the things that you need to know right off the top of your head. And I strongly recommend this being a thought process, not a memorization. Don't memorize each gland, each hormone, and what its function is. There is a memorization element. You do have to just be able to say the pancreas releases insulin and glucagon, but you want to try to ground that in some other type of logic. You want to think about each gland and you want it to be like second nature for you to go, oh, well, naturally that gland would release this. And then it's also natural to say, based on the function of whatever this is, here's the location where it would want to go. So your steps are, where is the hormone synthesized and released from? That's always the same thing. Wherever it's synthesized is where it gets released. So basically, what gland makes the hormone? And then where does it enter the bloodstream is another way of saying where is it released from the gland. So I'll go up to the nearest picture. If a hormone is released at the pancreas right here, where does it enter the bloodstream? At the pancreas. If something is released up here in the thyroid, it's going to enter the bloodstream at the thyroid. There's no way for it to magically be somewhere besides where it was made. I just noticed that I am on the last picture. So before the words, I'm on the last picture. I accidentally labeled thyroid twice instead of pointing out thymus. So if you can look where I am at and fix that so you don't get confused. I was really focused on trying to make sure you had enough room to write everything here. I will say this. You just need to know that the thymus exists and that it's located in the chest for now, because the thymus is really talked about as part of the immune system. So I have it labeled because it's always shown here, so I think it would be confusing if I just ignored it, but you don't need to study with the endocrine system for this. So make yourself a note somewhere. Just know that the thymus exists, what it sort of kind of looks like, and where it sort of kind of is. Know that it's part of the endocrine system, but it's really an immune function. So as far as the way that we study for what we're trying to do, you're going to learn about it with immune. So going back down to my written, where is the hormone made, therefore released, therefore enters the bloodstream? That's step one. So each thing, this is going to be a matter of knowing where is the gland located, what does the gland make, and that's step one, and you're done there. Once you're good at that, you can kind of picture the map of hormones in your head, and then you can say, what is the action site of the hormone? In other words, where does it go when it enters the bloodstream? It's got a destination in mind. Where is it going to go to engage in the chemical reaction that it's designed for? The function is what's going to answer that for you. Knowing what the hormone is supposed to do should tell you, in most cases, where it would go. So then the function of the hormone is the third step. You might have that as your second step, so you might focus on functions, then action sites, whatever makes more sense to you. But essentially, you need to be able to do a logical process. When they mention a particular hormone, you need to be able to say, oh, that's released by this gland, which is located, you know, in the chest or wherever it's located. Generally speaking, that's going to be a general. And then you're going to say it releases this hormone, which does this, and it does it here, wherever that is. So what a hormone does, where it comes from, where it goes, and what its chemical reaction is. That will avoid you taking this piece of paper and just trying to memorize the hormones. When you get a complicated question, which I can just about promise you, you will feel like any question you get pertaining to endocrine is a complicated question. It's never as simple as, what does the pineal release? It's always as complicated as, how does parathyroid hormone work to change blood calcium levels? It's always a complicated, involved question that combines your knowledge of several different things together and requires you to know several different things at the same time. And that's where this thought process really comes in handy. I'm going to do a couple of examples of ones that I think really help exhibit the thought process, so that you can take the thought process I'm applying here, and you can do it for everything. So I'm going to go back up to where my glands are listed. Let me erase all the chaos that I have here. So I'm going to talk about a couple of them that I think are particularly important or particularly difficult to get started with. One of the things that's really important, in fact, I would honestly say you have a 90% chance on the T's of getting asked about a particular batch of hormones. And that particular batch is the ones that are related to blood calcium regulation. It's the 3 that I just circled. I have this explained on its own page down later in the written part of the notes. You need to be able to think about blood calcium levels being too low and too high. And you need to be able to say, well, if the blood calcium is too low, here's the hormones that would release, and here's what they would do to fix the fact that the blood calcium level is too low. So you essentially have too low, otherwise known as hypocalcemic, and then you have too high, known as hyper. So you would need to be able to have a logical process built that tells you what each of these hormones does, when it would be active and when it wouldn't, and then how that would regulate blood calcium. Going down to the written part, let's see. So I have completely a page that's dedicated to blood calcium, because that is really important. And it starts right here. It's actually not on its own page anymore, so something changed in the spacing. So from here down, there are 3 hormones, the ones that we just circled, that are related to the regulation of blood calcium levels. Calcitonin, calcitrol, parathyroid hormone. You will need to know where each of these comes from, and they do each come from a different place. Parathyroid hormone comes from the parathyroid, so that one's fairly easy. Calcitonin comes from the thyroid, and calcitrol comes from the kidneys. That you just kind of have to know. So that's part of that very first line of study that you do, where you say, where are the glands, and generally speaking, what do they release? And then you need to know what each of them is active for. So hypercalcemia refers to the blood having too much calcium. And then hypo refers to having too little calcium. There's 3 major systems, major physiological systems that are involved in regulating blood calcium. So in addition to knowing there's 3 major hormones involved, there's also, separately and unrelated, there's also 3 body systems that become involved. Think about this for a moment, especially because we have talked about this a little bit before. What would the 3 systems be that would be involved in regulating blood calcium? When I've done tutoring over this, I would have to say that most of the time, most of my students, if they make themselves think what would be involved in changing calcium levels, usually you can list out at least some of it, if not all of it. So pause for a second, because then the video won't be as long. Pause for a second and think about what systems, you know, from integumentary to skeletal to endocrine to renal system or urinary system, which systems do you think might have something to do with changing and regulating blood calcium? So I'm about to give the answer to that. It is in your notes as well, but you want to be thinking about this so that you can develop the thought process. So pause if you still want to think about that. The three major systems that are involved are the urinary system, or the kidneys, the skeletal system, and the digestive system. The one you probably thought of right away was skeletal, because when you think of calcium, you think of bones. And that would be accurate. The skeletal system is most certainly connected to what your blood calcium is doing. So why is the urinary and digestive system involved? Think about that logically and think about why those systems would be the three that would be involved. Skeletal is reasonably obvious thanks to American marketing that has taught us over the years that calcium builds bone. So that one's kind of the obvious one. Urinary and digestive system are essentially filtration systems in a sense. The digestive system, and I have all this described here. So the reason that the digestive system is involved is that it decides what and how much to absorb into the bloodstream to bring into the chemistry of the body from what we eat. So the digestive system can let calcium move completely through and come out as waste and never absorb, or it can make sure that every single speck of calcium that is coming through gets absorbed, every little teeny tiny molecule. So those would be the two possibilities. And of course, in between there. So if we have blood calcium that's too high, the digestive system can decide, I'm not going to take in any more calcium so that that doesn't worsen the problem. If your blood calcium is too low, then your digestive system will focus on picking up every bit of calcium that it's got access to as it's moving through your digestive system. And then the kidneys, so separate thought process. Why are the kidneys involved? The kidneys make decisions on sort of the other end. So the other end of the spectrum where the body is deciding to let things leave that have either run their course or things that were taken in that were waste in the first place, like the Skittles that you ate. Your kidneys decide, is this going to leave or is this going to stay? What you know the kidneys as being really in charge of is water balance. So you know that the kidneys decide, do we want to let more water go? Do we have too much water? Do we have not enough where we want to save it? And calcium is one of the electrolytes. So it's one of the things that is not only controlled as far as level through the kidneys, it's also actually involved with water balance. So calcium being balanced is an essential component of water level being balanced. So the kidneys have the ability basically to excrete. Remember that with the kidneys, they've got their own word, which is excrete, or to not excrete any substance that is in the bloodstream. So the kidneys get access to everything that's in the bloodstream. They make a decision to keep or get rid of whatever's coming through. So if our blood calcium is too high, our kidneys can decide to excrete as much calcium as is coming through. If our blood calcium is too low, the kidneys can make a final decision not to let out any calcium, which will allow us to keep whatever we do have access to rather than worsening the low level. So these are the explanations of why those systems are involved. I will explain skeletal because it's a little bit deeper than just knowing that bones are connected to calcium. So the skeletal system makes and breaks down bone. Bone is made with calcium. So if you break down bone, you create raw calcium supply. So that'd be like if you took bricks and broke them into a million pieces, then you'd have a bunch of rocks that you could use for whatever you needed that material for. If you build bone, you're going to be taking calcium from the bloodstream, away from the bloodstream, to use as a building block to make bone. When we talked in Anatomy 1 and also in this review class, we talked about the fact that there's two major cell types. There's osteoblasts and there's osteoclasts. The blasts have a B in them. Blast is for building. The clasts have a C in them and they are for chewing. So if blood calcium is too high, we want to take calcium out of the bloodstream because there's too much in the bloodstream. So we could build bone and that could use up some of the calcium that's extra. If it's too low, we could break down some bone and send the calcium that is raw material from breaking down bone to put in the bloodstream and increase the level. So my biggest piece of advice, I used to have a hard time with blood calcium regulation, and I know that a lot of you do. I have improved my explanation of this 100 times, and it's a lot better than it ever was before. But honestly, I had to get really good at understanding it to improve my explanation of it, because this is very challenging. My one piece of advice, the one thing that took me from not being very good at all at thinking about these hormones to being really good at it to where I can picture every scenario, was focusing on blood level. If you try to focus on what are the bones doing, are they building or are they breaking down? Or if you try to focus on what is the digestive system doing, letting things come in or not letting, you'll always get confused. So you can't study blood calcium hormones by saying, oh, calcitonin does this, 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 and that. Calcitrol does this, 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 and that, and parathyroid hormone. You can't do it that way. What you have to be thinking about is the blood level is too high. So each hormone that's involved is going to have a role somewhere within these three systems in bringing it down. If the blood level is too low, then each of the systems, each of the hormones will have a role in raising the blood level. Always be focused on thinking calcium that's in the blood is either correct, in which case there's no question to ask, or it's too high or it's too low. So be picturing the blood and be thinking, am I trying to remove calcium from the blood because there's too much? Or am I trying to create calcium to put in the blood because there's not enough? That took me from, as they would say, 0 to hero on blood calcium hormone regulation. These questions are hard. They do ask about the hormone. So they would say, what would parathyroid's hormone be in? And then they'll give you some blood level type scenario. What you have to be picturing is the blood has too much calcium, so I need to take some out, or the blood doesn't have enough, so I need to put some in. So let's say that this is a little blood vessel. In this scenario, here's my calcium. So these are little dots of calcium. This is too high. And I'll draw the other picture real quick so that we have something to be relative to. And let's say that this is too low. So there would be something in the middle that would be more like just right, and it would be somewhat in between the two of those scenarios. There is no question that can really be asked if the blood calcium is perfectly balanced, because the hormones are not doing anything if it is. So we only involve the hormones when it's too low or too high. And we're talking about the level in the blood, taking up space in the bloodstream, flowing through the body as part of the cardiovascular system. When it's too high, we want to take calcium out. When it's too low, we want to put calcium in. If you always stop and look at your question and get into this place where you are thinking about the blood and you're thinking about whether our arrow would be pointing from the blood vessel out or from the systems that are outside the blood vessel in, this will ensure you can always answer your question. So down here, I have the actual hormones. Once you have a good understanding of what it's like for the blood calcium to be too high and what it's like for it to be too low, and how you would very generally need to regulate that, then you really have a place where you can really look at each hormone and understand. One thing you will have to have sort of memorized is each of these three hormones. Two of them have very similar names. One of them has a very different name. Unfortunately, the two that have very similar names are not identical in their function, which this is something I'm really aiming to make much clearer than it was in the original class. If you took the old version, you might be seeing this by the time there's a new version, and I did do a good job of it. But I wasn't focusing as much on blood levels when I originally taught this. So thinking about blood levels, you're going to have to kind of have memorized that calcitonin is active when the level is too high. So calcitonin would be active in this scenario. If pictures help you, you might want to label the hormones next to your pictures of your blood vessels. The other two, calcitrol and PTH, are involved in levels that are too low. Calcitrol is the one that comes from the kidneys. Calcitonin is the one that comes from the thyroid. I've never come up with a creative way to remember those based on where they're located and what their name is. If you have something, let me know. But you'll just have to remember which of the cal is located in one place, which of the cal is located in the other. PTH is used when calcium is too low, and then so is calcitrol. They do different things. The reason that there's multiple hormones involved in raising blood calcium is because they raise it in a different way. One of them also propels the other to come on more strongly so that more regulation can happen. So if the blood calcium level is higher than desired, that's the picture that we have on the left. So if it's doing this, calcitonin activates and it lowers blood calcium. So you can instantly remember that calcitonin lowers blood calcium because you know that it's active when the blood level is too high. So if something's active when the blood level's too high, that something must lower the calcium. If something is active when it's too low, that must be something that raises the calcium. Again, always focusing on the blood, never focusing on how much calcium is located in bones, how much is in the digestive system, how much is in the urinary system, just focusing on how much is in the blood. So calcitonin does a couple of things. When the level is too high, calcitonin stimulates osteoblasts. So one really good way to get rid of too much calcium in the blood is to use it. So if you have too much tea in your fridge, the best thing you can do is use the tea, which will lower the amount that you have stacked up in the fridge. So we want to take calcium from the system, from the blood, and we want to use it for something so that it's out of the way. So stimulating osteoblasts will cause bone to be built, which of course uses calcium. So blood will be giving calcium away, lowering the blood level so that you can build bone. An important part of stimulating osteoblasts is inhibiting osteoclasts. Those two are always going to be seen together. You're never going to see something that stimulates one of them but doesn't inhibit the other. That's a package. So anytime you're trying to stimulate blasts, you're also going to inhibit clasts by two different mechanisms that are happening at the same time. If you're trying to stimulate clasts, which you would do to raise the blood level, then you would need to inhibit blasts. When blasts become active, clasts are going to try to become active to try to balance what the blasts are doing. So inhibiting them is just as important as stimulating the other. When osteoblasts are stimulated, calcium is removed from the bloodstream to be used in synthesizing new bone. So the silver lining for calcitonin is it only does it really in one way. And there's really only one way as far as hormone stimulation that's going to cause a specific use of the calcium. Of course, our body is also going to be lowering digestive intake, and it's also going to be raising excretion. That just doesn't happen to be one of the functions of this particular hormone that you're supposed to know. But logically speaking, you know that there are 3 ways to change the blood calcium level. This is just listing what you need to know about what a particular hormone is doing. If the blood calcium level is lower than desired, we have 2 hormones that get involved. So we need to save all the calcium in the bloodstream, and we need to try to increase the amount that's coming in or that's available. Calcitrol comes from the kidneys. It raises blood calcium levels by acting on each of the 3 critical systems. So it will decrease calcium excretion by the kidneys. It will promote digestive absorption of calcium from food. So we're bringing in any calcium we possibly can. We're not letting any calcium out, which is 2 different systems. And we're going to promote osteoclast activity. So you would have to inhibit blasts, which I swore I had labeled here, but I don't see it. So just make sure that that is labeled here. So stimulating osteoclasts is going to cause bone to get broken down, which is going to cause calcium to be put into the bloodstream because now we have raw material that we're no longer using. Oh, here it is. I did write the inhibiting blasts. It's just later. So along with the promotion of osteoclasts, we are inhibiting osteoblasts. PTH, totally different hormone coming from a different place, is the most versatile and the most powerful of the blood calcium hormones. It will raise blood calcium by doing three things: preventing the kidneys from excreting any calcium, promoting osteoclasts so that bone is broken down, calcium is added to the bloodstream, and it promotes that. It promotes the release of calcitrol, which then repeats some of its mechanisms and has additional mechanisms. We call PTH the powerful one, P for PTH, P for power, because it causes calcitrol to become active. So the power, the reason I'm saying it's the most powerful is it activates calcitrol. Calcitrol has three mechanisms. So calcitrol is very, I don't want to say powerful because you'll get confused between the two, but calcitrol is very versatile. It can really make an effect on blood calcium levels very, very quickly because it has mechanisms on every system. So the fact that PTH does some of those mechanisms, but also releases calcitrol so that it can repeat the mechanisms, that will fix your low blood level very quickly. This is the type of thought process that you want to have. So you always want to start with, what is the problem that we're trying to fix? What does the existing issue look like? How does the hormone fix that is the second part of the thought process. So you want to think about what's happening actively that's actually going to cause the hormone to get released, and then what does the hormone do and where does it do it in order to correct the problem. Another good example, I'm going to go back up to the pictures part. Everything is listed here. There's page upon page describing the hormones. I just ask that you try really hard to use your diagrams a lot and really focus on what is the problem, what does the problem look like, why does the hormone fix it, where does the hormone need to go to fix it. You should be thinking of this on a process level rather than memorizing hormones. So what I would really encourage you to do, and I'm going to do another example or two and then we're going to go on, is use these blank diagrams, come up with the information on your own, and then check what you came up with by going down to this list and locating it on the list. So when you see ADH, antidiuretic hormone, its name kind of tells you what it does. So what I would encourage you to do is up here, you see that I have ADH labeled right here as antidiuretic hormone. Think ahead before you ever read what that is. Antidiuretic hormone would do what? Based on its name, it's logical what it would do. You can always pause the video for a second to think about the questions that I'm posing. I strongly encourage you to do that. So if there's any instance where you can come up with a thought process before I hand it to you, that's really good for your long-term understanding. So think about ADH for a minute before I give the answer. Pause the video, think about it, look at the name of it, think about what does it sound like it does. And then if you're correct about what it does, where would it want to go to do that? So pause if you're not quite there yet. I'm about to give the answer to that. So antidiuretic is anti, which is always the opposite of, and then diuretic. So knowing what a diuretic does is important here. Diuretics basically make you pee. They basically encourage water loss. Well, encouraging water loss by making someone have excess urine production has a very obvious system that it's involved with, which is the urinary system. So seeing the word diuretic, you should instantly go, oh, urinary system. Now this is anti-diuretic. So if a diuretic, which is like a medication, or there's some natural ones like coffee is a natural diuretic that causes you to lose water, so are certain types of tea. So anti would be the opposite of diuretic. Diuretic makes you pee more. It encourages water loss. Anti-diuretic is going to encourage the holding, the retention of water. So saving water as opposed to making more of it come out. Well, why would we want to do that? Because our water level is too low. If we don't have enough water and or there's not much water coming in, or there's not any water coming in, your kidneys really monitor that, and so does your brain. If it seems like no water is coming in today, then the kidneys might determine, well, we've got enough right now, but it doesn't seem like there's any coming in. We need to slow our processes down and make sure we're not losing anything. So when the water level is too low, this is where we were on blood calcium. This is where we need to be. What's the problem? The problem is that water is too low throughout the body, or we're concerned that it will be too low in the near future throughout the body. That's what's going to trigger ADH. So water levels being too low is going to cause our body to want to get more water circulating and just not let any go. And again, you can probably picture one major system involved with that would be the urinary, because we're basically going to do the opposite of diuretic. So we're going to discourage urine production. And instead of producing urine, we want to make more water come back into the bloodstream. So our goal here is more water in the bloodstream, and in turn, less leaving. So less water leaving is obviously the kidneys. They would decide to reabsorb water instead of deciding to excrete it. So the kidneys will decrease their excretion of water. There's another system similar to blood calcium, and you'll see that the same systems are involved in regulation of a lot of different things. Can our digestive system be involved in this? Obviously, your digestive system has the ability to let water just pass right through or to save it. So your digestive system can also be involved. It can also have a mechanism attached to ADH where it increases its absorption. If you have lots and lots of water and there doesn't seem to be any immediate concern about water, more of your water is going to move all the way through the digestive system without ever getting absorbed, and it's going to be used to make fecal waste to where you're not constipated, essentially. So if your digestive system is really functioning in this ADH pattern for a really long time, there is an effect on the other end of that, which is not enough water gets into the bowel, and it makes it where constipation happens. So constipation is a result of dehydration. That said, on a very temporary level, we wouldn't see much effect. We would just, for a very short period of time, because ADH is active, we would see the digestive system not let water through. Hopefully later it gets some extra water that it can let through so that it doesn't affect the bowels. But in the meantime, we can increase the water level of the blood. Remember, this is what we're trying to do. More water in the bloodstream, less water leaving. So we won't let water leave out the digestive system, and we won't let it leave out the kidneys. The digestive system will absorb more, and the kidneys, if they were in the process of letting water go away, they will reabsorb. So there's absorption and there's reabsorption. Reabsorption, we only ever hear that in reference to the urinary system, and that basically means that a last-minute decision is kind of made where something was about to leave, so it's in the tubules of the kidney, and then all of a sudden, no, don't let that go, so then it reabsorbs it back into the bloodstream and out of the kidney. So that's another hormone that you now have an example of. So we would think about, what is its action? Well, the action is right there in the name. It's anti-diuretic, so we're trying to save water. So the next thought process is, what systems can we use to save water? This time, skeletal would not be something you could picture really being directly involved in that. So that tells you which systems may or may not be involved. The next one under hypothalamus is oxytocin. That stimulates labor contractions. Again, these are all listed down below. So where would you go to stimulate labor contractions? You would have to go to the reproductive system, more specifically to the uterus. So it's obvious when you think about what something is supposed to do, what it ends up actually doing in turn with its mechanism. The last one I'm going to talk about, because there's one other thing I have to do with endocrine, and endocrine's going to take up a lot of our time, is pancreas. Pancreas regulates blood glucose. Again, bloodstream. Really, every single one of these has to do with, does the bloodstream have too much of something, not enough of something? or the right amount of something. Endocrine system becomes involved when there's too much or too little of something in the blood. The more you can be picturing the bloodstream, the better off you are with studying endocrine system. So in this case, blood glucose is what's too low or too high. When there's too much glucose in the blood, that's when insulin is active. So insulin's active when it's too high. When there's not enough glucose in the blood, glucagon would be active because it's too low. So what does glucagon do? Well, what would you do if glucose levels in the blood are too low? What you would do if glucagon, again, pause me anywhere that you want to think a little bit longer before I go on. What would glucagon do if blood glucose is too low? Well, raise the blood glucose, right? So how do you raise the blood glucose? Because we have stored sugar, which is part of insulin. One of the things that insulin does is it stores sugar. That sugar is then stored in various places and can be mobilized at any time. So what does glucagon do? It mobilizes stored sugar. So when we eat, we store sugar knowing that we don't know when the next time is that we'll eat, and we need a constant level of blood glucose. These two hormones regulate that balance. Insulin is active when we're eating. So glucagon is active between meals. Insulin is active while or shortly after eating. So when we're eating, we have way too much glucose in the blood because we're actively putting glucose into the blood on a constant level. What does the insulin do? It lowers blood glucose. How does it lower blood glucose? Well, the definition for glucagon helps you think about that. It lowers blood glucose by removing glucose from the blood, of course, and making it into storage molecules. Storage molecules are no longer in the blood, so that brings down our blood level without just wasting glucose. So we take in every ounce of glucose possible. We store the glucose that is excess. So insulin's function is to take it from the bloodstream, convert it into an inactive molecule, and store it somewhere. That prevents our level from remaining too high. Glucagon is active when suddenly it's been too long and the glucose in the blood is decreasing and now it's too low. Now we can go back to where insulin dropped off those inactive molecules and we can reactivate them and put them in the bloodstream. One more silly detail on insulin and glucagon. That's important, understanding that we're talking about blood glucose levels and we're talking about them being too high or too low. These are obviously yin and yang. They balance each other. We need both of them all the time because one of them stores molecules for the other to mobilize later. Something really silly that you need to know is that insulin is released from the beta cells, glucagon from the alpha cells. I need to go check the written section. I'm pretty sure I put that in the new notes, but it's very, very important. So let me make sure that it is there. Well, I got one of them labeled and not the other. I will probably have this fixed by the time you see it. But here I got secreted by beta cells. You just need to add, if it's not added already, secreted by alpha cells. So what they like to do is a multi-part question where it says insulin is released from the blank cells of the blank and it blank blood sugar. So you'd have to be able to say it's released from the beta cells of the pancreas and it lowers blood sugar. So use the same process for everything endocrine. You can always send me, if you kind of write out your thought processes and say, this does this, so it must affect this and this and this system. So its action sites must be here and here. You can send me that and I can look over that and I can be able to tell if you've got all your manufacture sites, action sites, and reactions labeled appropriately. One other thing that I want to mention, because it kind of needs to be explained, is at the beginning of the written section right here, where it says hypophyseal portal system and control of the endocrine system. I'm going to say this very simply. The hypothalamus controls the endocrine system. It has the highest level of control of anything in the endocrine system. So the hypothalamus, you could very well be asked, what gland controls all the other glands, or what gland is ultimately in charge of the endocrine system? And the correct answer to that would be hypothalamus. The tease is actually quite famous for not giving the best answer. So they'll ask something and then they'll provide the second best answer, but they won't provide the best answer. Don't know why they like to do that, but it makes the test harder. So if they said what controls the endocrine system, it would be a very real possibility that hypothalamus would not be there for you to pick. So that's where understanding that there's a two-step system to that control can really help you with your visual image. So the hypothalamus controls the endocrine system for one very specific reason, and that is that it can communicate with the nervous system. So the hypothalamus is the only endocrine gland that understands the language of the nervous system. That's why it's in charge. However, oddly enough, it's kind of like if you've ever worked with some experience in retail, there's like a general manager, right? So let's say a Kroger store, for example. There's a general manager who runs the entire store. They are the big, big, big boss. And quite honestly, no matter how often you go to Kroger, you have probably never seen that person. They work probably an 8 to 5 type thing. They might even work remotely a fair amount of the time. And the point that I'm getting to with the general manager is they delegate everything that they do. So they are just in charge. You're not going to see them stocking shelves. You're not going to see them telling, the cashiers to switch shifts or go on lunch. You're not going to see that coming from a general manager. You're not going to see a general manager because they have, assistant general managers, they have shift managers, they have shift supervisors, and those people are all underneath them to where those people are who actually put out the orders. So the order goes from the general manager to the assistant manager. The cashiers that are on the other end of the spectrum, they're going to hear it from their immediate supervisor. It's going to get passed down a few times before they actually hear it. That's the way the hypothalamus works. So as much as the hypothalamus commands everything that the endocrine system does, it doesn't actually send out its own hormones at all. It does not actually release anything directly into the bloodstream. You can make a note of this somewhere, maybe right here. So basically what I'm telling you is the hypothalamus doesn't release anything directly. It does release hormones, obviously, because we just talked about some of them. So directly is kind of the key word, into the bloodstream. That's important because we've been focusing on bloodstream. The hypothalamus releases hormones that then go into the pituitary. So the hypothalamus and pituitary are completely connected, and the hypothalamus, rather than having hormones exit out the hypothalamus itself, they go into the pituitary gland and they get released out of the pituitary gland instead. That is the hypophyseal portal system. So essentially, the hypothalamus is so much in charge that it doesn't actually lift a finger. It drops the hormones that it does have down into the pituitary. The pituitary is who actually sends them out, who commands them as to where to go and what to do. And all of that is controlled by the pituitary. So the pituitary is the shift supervisor who does the real work. However you want to relate that, hopefully you have an experience that kind of allows you to know what I'm saying with the general manager never being visible and instead people that are underneath it, because that's really how this works, is it's a delegation system. Because of that, they may ask the question, which of the following glands controls the endocrine system, and then not give you hypothalamus. If that happens, you want to pick pituitary because it is the second in command. You don't want to pick pituitary as controlling the endocrine system if hypothalamus is there, because hypothalamus is a better answer. It's who's truly in charge. That said, if you walk into a Kroger, you might see the pituitary gland or you might see the shift supervisor giving orders, And you might think, oh, that's the boss right there. But their orders are coming from somebody that you don't see, so they actually aren't the original source of the order. So the hypothalamus is the original source. If they don't allow you to pick that as who controls the endocrine system, and only if they don't give you that, then you would pick pituitary. So first in command is hypothalamus, second in command is pituitary. That's a lot of time spent on endocrine, which I intentionally did because we didn't spend as much time on it in the classes before. I strongly encourage you to really force yourself to be using those thought processes. I'm basically asking you to do it sort of what might seem like the harder way, but you're going to have a much better memory, a much better understanding. And the problem is the test is not set up where having everything under the sun memorized about the endocrine will actually allow you to answer questions, because they're systematic questions. They're saying if this happens in this location, what's going to happen in this other location, and who's going to bring on that reaction. It's very, very, very complicated. So you have to have a reference that you can pull yourself to, like the best reference being what is happening in the blood right now. Okay, if this is what's happening in the blood, then this hormone is going to get involved. These systems are going to get involved, and this is what's going to happen. Reproductive, very, very, very simple. If you don't remember the concept of like gametes and germ cells and all that, you do need to go back to the beginning of Anatomy 3, because I'm not going to go into a lot of detail. What you have to know for reproductive is super limited. You need to know that the gametes are what manufacture the germ cells. You need to know that the germ cells are the actual reproductive cell that carries the information for offspring. You need to be able to tell the difference between a gamete and a germ cell. So the gametes are ovaries and testes. Those are the manufacturers. The germ cells are sperm cells, germ cell, sperm cell, they rhyme. And then eggs, which are technically called ovum. Ovum come from the ovary. They are nicknamed eggs. So the germ cell, remember, is created in the meiosis process. Very important part of reproductive. Meiosis, which has the letter E as its second letter, which is a coincidence with the word reproductive having an E as its second letter. Anytime we're talking about the reproductive system, it's meiosis. Anytime we're not talking about the reproductive system, it's mitosis. Mitosis is cellular copying. So mitosis with a T is cellular copying. What you might think of when you think of mitosis is stem cells. And again, there's a letter connection that mitosis and stem cells both have T's. Meiosis and reproductive both have a second letter of E. That's the most important thing. Meiosis is where a new being is created. It's not identical to the original cell. It's a combo of two different cells from two different people. And then mitosis is just when your normal everyday cells, like your liver cells or your kidney cells, copy themselves so that they can replace the cells that are getting old and that are no longer functioning. You need to know that the fallopian tubes are the site of fertilization. So where the actual fertilization process happens is in the fallopian tubes, which also means that that's the site of meiosis. So fallopian tube starts with F, so does fertilization. That's the easiest way to remember that. Fallopian tube is the site of fertilization, which means that it is also where meiosis begins. There is still a question floating around about the cervix being the hollow, the way that they say it is hollow muscular tube that connects the vagina to the uterus. That's an active question. And then the last thing for female reproductive is the idea of the corpus luteum, which is also included in endocrine. So the corpus luteum is essentially a like a structure that forms. And when ovulation is happening is when we see that. I'm going to zoom as far into this as I can here because there is a picture of it. So the corpus luteum is this little structure right here. It's only present in ovulation. So you need to know that it exists. Typically, they actually do describe to you that the corpus luteum is a structure that does appear during ovulation. So they might actually give you that part. What they're going to want you to understand is, what is that for? So this forms during ovulation. What does it do? Well, the main thing that it does is releases a ton of progesterone. There's two, whoa, that's what I was kind of afraid would happen. There we go. There's two reproductive hormones for women, which are estrogen and progesterone. It is very important that you know why these are not at all the same. So if you couldn't tell me off the top of your head right now why estrogen and progesterone are not the same thing, that is somewhere that you need to focus. Progesterone is essentially, if you just put all of progesterone's function in a few words, is it readies the uterus for pregnancy. So all the things that happen in the ovulation process, progesterone and ovulation go hand in hand. So at the actual moment where the egg has reached its full maturity, it's dropped into the fallopian tubes, it's wanting to be fertilized, it gets fertilized, that's when progesterone is active. I always try to think of this as pregnant, starts with a P, progesterone. I would love to know if you guys think that the letter thing is helpful, because that's just something I've always done. My brain has always kind of thought of like, oh, that's P and that's P, or that's T and that goes with T over here. But let me know if you think there's so many of those that it doesn't help, or if you think that it helps, and I will try. If you think there's too many of those and it's too hard to remember them, I will try to do a better job of creating better, newer ways to remember that. So progesterone pregnancy, it's actually not just P, it's PR. Progesterone pregnancy has everything to do with the ovulation cycle happening, what happens right before and right after ovulation, everything to do with that moment in time where pregnancy can happen. Estrogen is before that. So estrogen is before pregnancy. Alphabetically, estrogen is before progesterone alphabetically. So if you think of that as why it would be first, it is going to promote the egg maturing in the first place. So if the egg never got fully matured, it would not matter if there was a perfect timing where the egg was in its fertilization spot and a sperm cell made it to that egg. It wouldn't matter because the egg was not ready to be fertilized and undergo meiosis. So estrogen is on the back end. It's the behind the scenes hormone that's making sure that the egg does reach its full development and that it is ready by ovulation to do so. Once ovulation is ready to happen, then it's all progesterone. Estrogen is going to reactivate to mature the next batch of eggs. Definitely you need to know that corpus luteum releases progesterone and that those are going hand in hand. And that's a structure, basically a hormonal structure that forms during ovulation, disappears the rest of the time. There are two things that the progesterone that's coming out of that corpus luteum does. One of them is essentially it readies the uterus for pregnancy. Usually how you see that on the test is they'll say that it thickens the endometrium. So as a review of some basic physiology, the endometrium is the layer that lines the uterus, and throughout the monthly cycle, it gets thicker and thicker and thicker, reaching its maximum thickness when ovulation would occur and when there's a chance of pregnancy happening. If pregnancy does not happen, then that's what causes the menstrual cycle, is it sheds that whole big layer, starts right back up at the beginning and makes a new one. And then again, the new one gets to its absolute thickest, ovulation happens, and either pregnancy occurs or it doesn't. And if it doesn't, the menstrual cycle goes on again. Obviously, those are somewhere nearby a month apart. So readying the uterus for pregnancy would involve a few things, but the one that they like to focus on is thickening the endometrium. So progesterone is the hormone that wants you to be pregnant. It wants to encourage pregnancy to go well and fertilization to go well. So thickening the endometrium as we're reaching ovulation is one of progesterone's important functions. The other important function is if the egg actually does get fertilized, it's going to speed the egg up. So it's once an egg gets fertilized, it's important that it runs very quickly from the fallopian tubes to the uterus where it's safe, and then the whole implantation process can start. So increasing the speed would also be a function of progesterone. Be very careful, because increasing speed of a fertilized egg is not the same thing as encouraging fertilization to occur. So here's what you don't want to pick for progesterone. There's something where they say something essentially like increases odds of fertilization. Progesterone does not increase the odds of fertilization. And they will always have like that and then thickening the endometrium. The only two things you want to pick for progesterone are the two things I have here, specifically speeding up a fertilized egg, which is already fertilized. So speeding it up does not increase odds of fertilization. It's already fertilized by the time progesterone comes along, or prior to ovulation, thickening the endometrium. Increasing the odds of fertilization is not something that you can answer just because a certain hormone is there. So basically, you would not end up with a test question that could really ask for that answer. One more thing on females that I just want to add a note to, because I kind of have a feeling that soon we're going to be seeing this. HGH, which I will spell out as I talk about it here, is the pregnancy hormone. A very easy question for them to catch you off guard with would be, what is the hormone that would show in a pregnancy test? That is surfacing on some tests, not the T's and the HESI at the moment, but I bet you it will in the next couple months. So this is the pregnancy hormone. A common question, like in anatomy classes or in nursing school, is why can we just take a store-bought urine test and be certain that somebody is or is not pregnant? Because HGH hormone is literally not present at all unless pregnancy has begun to occur. So if there is HGH in the system, whether it's in blood, whether it's in urine, blood is always more accurate, but urine tests for pregnancy are amazingly accurate. This is why. If there are traces of that hormone to be picked up, there is fertilization that has occurred, there is a meiosis process happening, and you are theoretically pregnant. Male reproductive, same thing on knowing the gamete and germ cell concept. I already went through that, so I won't do it again. And then the duct system. So the duct system is listed in order right here. You need to be able to put that in order. From the moment that a sperm cell is being made until the moment that that sperm cell leaves the body, what are the steps that it takes? What's the pathway that it follows? So it goes through the testes, it goes through the epididymis, it goes through the vas deferens, and then it comes out the urethra. The urethra has a couple of other important things that you need to be familiar with. One of them is that the urethra is a shared tube with the urinary and reproductive systems. That's still a common question. Still, that gets asked all the time. And then because that tube is shared is why the bulbourethral and or nickname Cowper's gland, that's why it exists. So because we have a shared tube between urinary and reproductive systems, which obviously focus on moving through very different substances, the bulbourethral gland is who cleans out the urethra in between different substances coming through. So essentially what the bulbourethral or Cowper's gland would be described as doing is releasing enzymes that clear excess urine from the urethra, keeping that tract clean for when the reproductive system decides to use it. They could call it either Both of these are accurate. They can't put them both there and make you pick between them, so you'll just see one of them. That exists because of the urethra being shared, and that's an important thing to understand. We would not have that there if it weren't for that. And then it releases enzymes that clear the excess urine. So the enzyme part of that is also important. Male hormones are super easy. They're included very detailed in endocrine. Testosterone's basically the only one, and testosterone encourages sperm production and hunger responses. In your endocrine notes, there is lots of involvement between the pituitary gland and the reproductive glands. And the pituitary gland is who basically releases all the different hormones that stimulate reproductive hormones to be made. So the pituitary gland is very heavily involved in the reproductive hormones being produced, not being produced or being inhibited, being produced in greater or lesser amounts. Those all connect back to the pituitary. That is very much endocrine. There's no way we would ever have time, even in an exclusive class on endocrine, to go through everything, but you will see it as you are focusing on your thought processes to get to that point. The next system in here is urinary system, and right up at the top, I have know your 4 byproducts. You wrote notes during Anatomy 3 class on this. I won't really go into a lot of detail on it again because you wrote out a chart, and that's still going to be the best thing to use. But essentially, you need to know what your 4 byproducts are. A reminder, byproduct is the non-desired outcome of a chemical reaction. So our body is constantly doing chemical reactions. Some of them involve the endocrine system, some of them don't. And every time a chemical reaction happens, we have our reactants that we put into the reaction. We have our products, which is why we did the reaction, was to get whatever those products are. And then we have some products that we didn't exactly want. They may be toxic and they may not. But those are always going to be referred to as byproducts. So there are byproducts that are totally not harmful to us and they can stick around if they want to. And then there's byproducts that totally are harmful to us. And that's where the kidneys come in. Their job is the ones that are totally harmful to us. We get them out of the body as quickly and efficiently as we can. And that's the center of the urinary system. That's why we always talk about urinary system with excretion. So basically, the urinary system excretes byproducts from all of our chemical reactions and then regulates water. There's a few things that they might ask you about in relation to the urinary system. What does it do in general? So that's what these underlined pieces are here. Helps maintain water and electrolyte balance, acid and base balance. This is very important wording-wise. Removes nitrogen-containing waste. When you see the word nitrogen and you see either nitrogen-containing or nitrogenous wastes, you know that's the kidneys that we're talking about. The other thing you should know when you see nitrogen or nitrogenous is that it's the result of protein breakdown. When you look at a chart of how the different macromolecules are made in the first place, protein stands out because it has nitrogen in it. Carbohydrates and lipids do not have nitrogen. Protein does. So when you see nitrogen or nitrogenous, you know 2 major things right off the top of your head. One is that protein got broken down and put off nitrogen because it was part of the protein. The other is that the kidneys are going to be in charge of filtering that out. Nitrogenous wastes are absolutely toxic, some of them more than others. So protein breakdown processes, and you know that most things in the body are protein, so that's happening all the time, constantly. That's what the kidneys are in charge of. So the 4 major waste byproducts, you have a chart for this. I strongly encourage you to go back to that chart and study back over it. You have ammonia, which is super toxic. Ammonia starts with the letters AM, and so does amino, and that's a good way to remember that ammonia is created when amino acids are broken down. That happens in the liver. Quickly converts to a less toxic chemical, which is urea, Urea would be the result of breaking down protein. So you'd have to break down a protein first to even have the ability to break down an amino acid. So a protein gets broken down, and it gets broken down into amino acids. So we break a protein down into amino acids, and then amino acids can be broken down, and we would get ammonia. Whoops. I'll put my A down there. And then this would put off urea. So protein getting broken down puts off urea. If we then decide we're going to keep breaking down what we just broke down, now we're taking amino acids and basically dissolving them into nothing. Then we're going to wind up with ammonia, which our body is then going to convert back to urea. And then the other two are much less important as far as you knowing what they are, how they're created, where they're created, and how toxic they are. So the ammonia and urea, you need to know all the things I just very quickly listed off, is uric acid and creatinine. They are both the result of nucleic acids being broken down. Nucleic acids would be in the nucleus of cells. So if a cell gets old, it's done with its life cycle, it needs to be broken down. We're going to put off one or both of these. And again, the kidneys are responsible for that. But you know that almost everything in your body is a protein, so you know you're producing a lot more ammonia and urea than you are uric acid and creatinine. They're also more toxic, and they also just so happen to be more prevalent as far as test questions. One very important thing to remember, I'm saying this all very similarly to how I said it in the other class, but not exactly the same, so that you can think of it slightly different, but truly the way we studied this in the other class is the way that we want to study this. Remember to focus on the blood. I don't even know how many times I've said that in this class. I'm kind of realizing as I'm doing this class the way that I am, how much I need to emphasize that when I do these classes next. You should always be thinking about the blood, which kind of means you're always thinking about how the cardiovascular system relates to whatever other system. Blood is what the kidneys are purifying. So just like every other system, there's blood running in and out all the time, constantly. Blood is always running in and out of all the different systems. When it goes through the urinary system, it's getting filtered from anything that shouldn't be in it. So if the digestive system is breaking down proteins and it puts off urea and ammonia, that needs to get picked up as the blood goes through the digestive system. And then that will end up in the urinary system eventually. The urinary system will see, oh, there's urea in here. That's not good. It'll take it out and send the blood back without the urea in it. Albumin is a protein that is found in the blood. That's seen in the cardiovascular notes. Healthy kidneys do not allow that to be lost. So this is another side note that I talked about in class. Know that if albumin is in the kidney or is in the urine, the kidneys are not functioning properly. So albumin being in a urine sample is a bad sign. The cardiovascular system regulates blood pressure in connection with the renal system. So if we have a lot that we need to purify very quickly and urgently, your blood pressure and pulse will be higher. If we don't have as much and we're in a nice groove and a nice balance, your blood pressure and pulse will be more normal. So your renal system has the ability to crank up the output of your heart with the intent of getting more immediate access to the blood so that it can be filtered. Renin is the hormone that does that. I forgot to fix this. Hopefully I'll remember to fix this. Renin should be up there because I'm describing what renin does. Renal arteries deliver oxygenated blood containing toxins to the kidneys for purification. Renal veins return deoxygenated but purified back. So think about why these two things are important. There's always arteries. There's always veins. We talk about them with cardiovascular system, but the reason that arteries and veins are important is because arteries take blood from the heart to every other place it needs to go. Veins return blood from every place that it went back to the heart again. We obviously think of that a lot with the oxygen and CO2. That one I don't talk about as much because I know that you guys know that really well. Arteries are supposed to deliver oxygen. Once the oxygen gets delivered, CO2 also gets picked up and the veins take back the CO2. when you're thinking about any of the body systems that's not the cardiovascular system, you have to swap the perspective that you are thinking from. So when you're thinking about the kidneys, the artery would be what's bringing in blood. So when you think about the heart and the cardiovascular system, you picture an artery as what's leaving. It's leaving the heart. When you picture the system that it's coming into, the artery is what's coming in. So the kidneys, just like every other organ, they need oxygen and they need to get rid of their CO2. So every cell in your body uses oxygen and creates CO2, kidneys being no exception. So you kind of have to hold two different processes in your head in two different places. One of them is, just like everything else, the kidneys need to get oxygen and they need to send back their CO2. In the midst of that, right smack in the middle of that process, is where the purification happens that the kidneys are supposed to do. So the way that the process works is kind of down here. You have an afferent arteriole that has the AFF prefix. That means it happens first. EFF means it happens second. Afferent arteriole, remember that eole is basically the narrower versions of the arteries. So you would see eole when it's coming into an organ or a tissue. So it's going to use the highways, the arteries, to get close to its approach site. Once it gets close, it's going to use the little neighborhood streets, or the arterioles. That's going to bring in, so thinking about the kidneys and where they lie in all the systemic processes, this is toxic blood that's coming in. So blood that comes into the kidney is coming into the kidney to get purified, so it is toxic to begin with. But it is oxygenated. So we're doing two things at once. We're bringing oxygen. We're also bringing toxins with the hope of getting rid of them. So the afferent arteriole brings in toxic blood containing oxygen. The first thing that happens is the filtration. So filtration happens before oxygenation. Very, very important to know that. Because that will help you not get mixed up between these different things. So the afferent arteriole brings in toxic blood that's containing O2. The very next thing that happens is it reaches the efferent arteriole, and that's going to take now filtered blood, still containing O2, and we know it still contains O2 because it's still an arteriole, not a vein or a venule. And then out of the glomerulus, remember that the glomerulus is where filtration happens. So the process is the blood enters the very beginning of the kidney. It gets filtered first, switches arteries along the way as it goes into the glomerulus for filtration and back out with filtration complete. Then, and you might actually add this right here, then the renal vein, hopefully I'll remember to add these things so that you're thinking that these are already in your notes. The renal vein would then take out CO2. So the renal vein, hopefully I remembered to add this, and this is actually in your notes right now. The renal vein takes CO2-rich blood back out of the kidneys. Hopefully I wrote that on your notes. It's always really hard when I teach a class this long to remember all the corrections that I want to make, but I will do my best. The last three things are the ones that are obvious, so I won't go back into those. Remember that the nephron is the functional unit of the kidney, but the glomerulus is the actual filtration center. That's another one of those things, just like a lot of these questions, where they can get you to use the very specific answer or the slightly broader answer. They won't pit them against each other. But glomerulus is who really, really, truly filters. Nephron is the whole unit that is responsible for moving stuff through and filtering it both. When you think about the kidneys and you think about blood filtration, the nephrons are what really do the blood filtration, and they do that because they have the glomerulus within them. Digestive system, I am not going to focus on a lot here because I know that this is written in a way that if you've read this a few hundred times, and you probably have, it really says everything. I redid these notes not all that long ago, and I really made them where they follow the flow exactly the way that it really happens. So remember that you need to know the 4 functions of the digestive system. That's true for every system. So I will stop here to remind you, you should always know the big functions of a system before you ever try to do anything else with it. What does the digestive system primarily do? What are its responsibilities in the spectrum of how the whole body works? Then you can go into specifics. So we ingest food, we digest food, we absorb food, and then defecation occurs with anything that we couldn't use that came through with the food. Peristalsis, very important, are the smooth muscle contractions that are moving the food through the digestive system. So remember that smooth muscle tissue is muscle tissue that is involuntary. You could not move food through your digestive system without lots and lots of muscle contraction happening. And then remember that motility with an ITY on the end is the speed that peristalsis is happening. Motilin, IN as a suffix usually indicates a hormone. So motilin is the hormone that is in charge of deciding how fast the food is going. Connect this back to the nervous system. I actually did a decent job of this in class considering how limited our time is when we're doing so many systems at once. So I highly encourage you, I really always highly encourage you to go back to your original classes. I don't encourage that with something like reading because you can only see a passage for the first time once, and then it doesn't have the same effect after that. It's very easy for you to hear new things if you go back to your anatomy lecture. So if you don't remember our conversation about how the sympathetic and parasympathetic nervous systems are related to this, I would strongly recommend going back. I'll try to do a good quick summary here. The nervous system is who's in charge of how motility is looking because parasympathetic is the rest and digest system. So as much as resting makes you, whoa, that always happens when I hit the edge. Hold on. So as much as resting makes you think of slowing everything down, motility would be at its highest if our body is truly just focused on digesting food, and that's it. If you're just 100% focused on digestion, it's going to happen much faster. Motility is going to be much higher. The muscles are going to contract much faster and much stronger, and digestion is going to be all that your body's doing. If there is some kind of sympathetic activation, sympathetic is the fight or flight system, so we can't really control when that might become active or not. Then that would slow motility because it will pull resources away from digestion. And we only have so much blood flow. We only have so much ability to contract different types of muscles at the same time. So if we pull resources away, motility will get decreased. Motilin is a hormone that increases motility. So that would be active when parasympathetic is active. So make sure, and I'm probably going to end up doing a supplement video at some point of talking about how the systems actually come together and connect. But I mention it anytime that it is directly relevant to you in taking these tests. I always mention it if it's an appropriate connection that I think you can understand at the time that I think of it. So nervous system, you've got a specific nervous system that is active alongside the digestive system, that promotes the digestive system. So it is very important that you think about how parasympathetic and in turn how sympathetic activation would affect these different digestive functions. It's also important to be able to just like basically recite all of the steps that happen within the digestive process, which is a lot. It's quite complicated. But essentially, you just need to follow the steps on that. So steps in the digestive process, food enters the mouth, needless to say, you know how that starts. Mechanical breakdown versus chemical breakdown, very important. So mechanical is like physical, it's muscle contraction, it's chewing, it's swallowing, it's things that are totally not chemical reactions. So your teeth are obviously a big mechanical breakdown mechanism, but so is saliva. If you're not talking about enzymes that are in saliva, if you're just talking about moistening the food so that it can get swallowed, that is mechanical. Chemical action by the saliva is when the salivary glands release amylase, which is for digestion of carbs. couple of notes here. I've had some questions recently where the question just gets asked a wee bit differently. And I've had a lot of situations where someone felt like they shut down and they didn't know the answer. So I'll clarify a couple of things. Remember, starch is one of the things they can call a carbohydrate. Starch is a type of carbohydrate. It's the most complicated of all of the carbohydrates. So if they said, what is the enzyme that digests starch? That would be the same thing, the same answer as what is the enzyme that digests carbohydrates. So that's one clarification. The other clarification is the salivary glands. So one of the things that I mentioned in the endocrine notes that is very important is the difference in an endocrine gland and an exocrine gland. An endocrine gland, endo means within, so an endocrine gland releases something into the bloodstream. An exocrine gland would include the salivary glands. It would also include the glands of your skin. It has a duct equaling an exit. So a salivary gland, the point of a salivary gland is to take saliva and mucus and release them to where they can freely flow in the mouth. So they are exocrine glands. They are sending their substance out. A duct is another way of wording like an exit. So an endocrine gland would just go straight into the bloodstream like that. An exocrine would actually have a tube that took it to an outside destination outside the body. So that's an exocrine, that's an endocrine. Your endocrine and exocrine glands are highly active in digestion. Both of them are absolutely imperative to the digestion process. So a couple of the things that I've seen in relation to that, one of them might say if the parasympathetic system is active. They always do this connection between parasympathetic and digestive. So that's very important to make sure you have thought about that in advance. If the parasympathetic system is active, what is a hormone that's active? What is an enzyme that's active? So they can ask the question, which of the following would be active during parasympathetic action? Well, anything that's on this list. So anything digestive, any digestive hormone or enzyme could arguably be said to be active during parasympathetic modes. Parasympathetic is focused on digestion. Digestion has countless hormones and enzymes involved with it. And what you'll see in the answer choices if they ask you that is that just one of them from this list is mentioned. The other ones are going to be like epinephrine, which would not be active during parasympathetic. Renin, which has nothing to do with parasympathetic. So the other answers are not going to be from this list. So the answer that I usually see for this is amylase. So they'll say, which of the following would be active during parasympathetic mode? And amylase is the only digestive one that's listed. They could also ask you what glands would be active. So just like any digestive hormone or enzyme would be active in parasympathetic, any digestive gland would also be active if you're in parasympathetic. So essentially, parasympathetic being active should cause you to picture this note page because that means the digestive system is being focused on. So they could also have you say that salivary glands would be active during parasympathetic activation. So you should just be thinking of parasympathetic just essentially means that digestive is active. So all the hormones that you know to be associated with digestive are active. All the enzymes you know as digestive are active. Any gland that's releasing mucus or saliva or anything else within the digestive system is active. So if you've had that issue, hopefully that clarifies that. Remember that they can ask things 1,000 different ways. And remember that my classes teach absolutely everything you're supposed to know. So when you see something that seems unfamiliar, it's not. As long as you made it through everything you were supposed to, it is not unfamiliar. It is just being worded a bit differently. So the idea behind intense review and supplement classes is to help you build those bridges more with my help. But you can also build those bridges on your own because you know that one system in one part of the body is active alongside another system in another part of the body, and they're going to have you connecting them together. Let me see if there's anything else in this segment that's important. Most of this is as clear as it's supposed to be. We did talk about insulin and glucagon with endocrine because they are part of the endocrine system. So that's an example of where hormones are active with digestion. So I won't go back through them, but they are listed here and in endocrine. Both are important. There is a fair amount because this class is reviewing so many hours worth of lecture. It's very important to look at all your notes from this class. This class is not designed where I'm going to say everything that I should say. So go back through digestive. There's lots and lots and lots of really good endocrine notes that we didn't even touch on. Make sure you go back to those. I'm not going to put a lot of time into digestive because I really feel like this is written crystal clear, and most of you do very well with this with the limited lecture that we did in Anatomy 3. Remember, if you would like to hear the digestive lecture again, if you'd like me to walk through these 7 steps again, that you can go back to your Anatomy 3 video for. It would be the last system covered in Anatomy 3, so it would be the second half or the last third. Moving to, and you also have a diagram, you can label things for that if you'd like to. Moving to respiratory, we have 3 more systems: respiratory, cardio, and immune. These are going to be the fastest 3. So you do need to know, I did put little marks. You'll notice I put all kinds of helpful hints throughout these notes because this is an intense class to tell you what to focus on. You need to know all the structures that are involved with respiratory. You also need to understand the ciliary escalator concept. I talked about that at length in the lecture, which is Anatomy 4. We're now on Anatomy 4. So the ciliary escalator is this combination of, here's the inside of your throat, here's the little cilia, which are like little hairs, and they can catch things that are not supposed to be there as they go by, like a dust particle. And then mucus is needed and released to be able to grab something off of there, and then the cilia can help it move up the respiratory system. So make sure you understand the concept of the combination of cilia and mucus and how they work together. So the cilia are like little hairs that can swing back and forth, which can propel mucus upward. That's why when you're sick, you have tons and tons of mucus trying to come up, is because it's carrying pathogens and your cilia are helping propel it up the throat with those pathogens rather than having it make it into your body. But there's a back and forth because cilia can end up catching particles because they're in the way. But they can't move them on their own. Mucus has to come encapsulate and grab whatever it is, but the mucus doesn't have legs, so then it defers back to the cilia needing to propel things upward. If that doesn't make any sense, you probably need to go back to the original lecture on that. It would take me forever to redo it, but it is in the beginning of Anatomy 4. One of the things I'm going to put emphasis on here is the ventilation process. You need to know the ventilation term. So I have it pointed out here. So movement of air in and out of the body is ventilation, and ventilation is the result of muscle action and negative pressure. So inhalation involves, this is something I added right here because there's a new question that words things just a tiny bit differently. So inhalation would increase the size of the thoracic cavity. That's one of those things that most of you kind of realized just because of this, because of what you already did in Anatomy 4, but I had a few questions on how that connects. So I guess the new question, instead of just asking like who's responsible for what, it asks what inhalation or exhalation does to the size of the thoracic cavity. When you bring in air, that expands the thoracic cavity. Your chest is bigger when you just took in a bunch of air than when you just breathed air out. So inhalation would result in an increase to the size of the whole cavity where your lungs are, and then exhalation would be a decrease in the size. So air being breathed in literally expands the chest. This part here is the same thing that I taught before, but I'm going to go back through it. One of the common questions is essentially, I guess basically the question of what actually causes us to take in air or to let out air. What actually causes that is the diaphragm. So there's two sets of muscles that are involved in respiration. One of them is the diaphragm, the other is the intercostal muscles. The question that they are essentially posing for you is to find out, do you understand that the diaphragm is a much bigger, much stronger, much more powerful muscle, and the intercostals are much less powerful, much smaller, and they are for support. So the diaphragm is the power behind respiration. The intercostals are just support. All the intercostals do, they're the little muscles between the ribs. They just help pull the ribs out a little tiny bit. The intercostal muscles in and of themselves do not make respiration possible whatsoever. So if your diaphragm did not work, you would not breathe. The intercostal muscles do not have the ability to take over respiration. So the question that they essentially pose is, which set of muscles is truly the reason that respiration happens? And that's going to be the diaphragm as opposed to the intercostals. And then they'll ask you to be able to distinguish between inhalation and exhalation. So inhalation is going to be when the diaphragm contracts. The diaphragm contracting causes negative pressure. So the diaphragm contracts and it actually pulls downward, and that creates a vacuum effect. You can add that if you would like to add vacuum effect. Because the diaphragm is lower than it normally is. So it opens up a space and it pulls air into that space like a vacuum. That is referred to as negative pressure. So inhalation would involve negative pressure, and it would involve contraction. And if you want to make a simple little list, now that you've heard this twice, or you will have heard this twice, you can kind of make a little bullet list. Inhalation is negative pressure. So in turn, exhalation is positive. Positive pressure is pressure exiting your respiratory system. Negative pressure is pressure entering. Inhalation is caused by contraction. So in turn, exhalation is caused by relaxation. And then both of them are really caused by or propelled by the diaphragm. So this is a little bullet list. I would not teach this way if this was the first time you heard it, because there's a lot more to it than memorizing words. But if you've been thinking about contraction and diaphragm and how the cavity expands and how it contracts, then this little bullet list might help. The thoracic cavity with inhalation. Hopefully you have more room than me, so you don't have to put this on the side in some awkward spot like I'm doing. But that would be to expand. And that would be, why can't I think of what the opposite of expanding is? Collapsing? It's not really collapsing. So let's just say decrease cavity size, because you don't collapse your thoracic cavity. If you know of a word that's opposite of expand besides collapse, let me know, because maybe I'm just totally not thinking. That's basically that part. The other thing I want to cover, there's one quick note right here. Breathing is controlled by the medulla. That continues to be one of the very simple questions that they ask. So if you know that the medulla of the brainstem, or even really if you just know that the brainstem is responsible for very critical, life-changing, life-altering processes that are involuntary, like breathing and heartbeat, then you should be good. So brainstem does breathing. It does the heart. Essentially, the brainstem is the thing that causes all of the autonomic systems to function. There is no such thing as an injury to the brainstem. If the brainstem gets affected literally at all, it would cause instant death. The other thing you need to know is, how is the brainstem contributing to breathing? So obviously we're in the respiratory notes. The main focus here is the breathing part of the medulla. So they may ask you who's in charge of breathing, and it may either be brainstem, which is the broad answer, or it could be more specific and they could actually name the medulla. I would be ready for both. So the medulla is one of the three parts of the brainstem. It would be fair to say breathing is controlled by the brainstem, but if you had medulla there, you would want to be more specific and say medulla. The way that it does that is the opposite probably of what you normally think. So the medulla controls respiration by watching for high CO2 levels. There's a really huge difference in watching for high CO2 levels versus watching for low oxygen levels. So watching for high CO2 is how breathing is regulated. That's why hyperventilation, where you're breathing in way too fast and taking in way too much oxygen, is extremely hard for your body to correct, because your body regulates and changes your breathing when there's a ton of CO2. If there's a ton of O2, your body doesn't even really notice that. So remember that the medulla not only controls respiration, it does that by watching for the CO2 level to get too high. It also watches for your blood pH to get too high. So as you're taking in more and more oxygen, your blood pH is changing. And essentially the best way to think of this is your body monitors for toxins. So your body doesn't monitor to make sure you have enough of the good stuff. The body monitors to make sure you don't have too much of the bad stuff. I'm going to write what I just said because I feel like that's probably a really good thing for you to have. So the body in general, not just talking about respiration, but that's where this came from. So the body regulates by watching for too much of a toxin. And I'm going to put quotes around too much of a bad thing. So your body is looking for a bad thing piling up and being too prevalent. Rather than, so what it doesn't watch for is enough of a good thing. Your body looks for poisons. It looks for toxins. It looks for harmful byproducts. Your kidneys operate based on urea levels getting too high rather than operating on water being high or too high or not high enough. It's the toxins that are being watched for. You can pause this if you want to write that down and you're not done yet. Last thing here that I want to cover in this review is COPD. So there's two types of COPD. You really could get asked about either of them, but I tend to see emphysema a little bit more than chronic bronchitis. It is critical to know the difference between them. So chronic bronchitis is the inflammation of the bronchi with swelling and excess mucus production, and it happens because of the loss of cilia function. So you have that ciliary escalator that is a 50-50 balance between the little cilia that can propel things and catch things and the mucus that can grab things and carry them upward. When you don't have enough of the cilia functioning anymore, the mucus wants to try to compensate for that by making more of the opposite part of the escalator. That is not a good situation, but that is our body's natural reaction. So if you don't have the 50-50 of the cilia and the mucus, you wind up with too much mucus. That's how chronic bronchitis looks. Emphysema is the alveoli. So there's a huge difference between the bronchi having too much mucus coming through them and the alveoli having a decrease in function. Alveoli are the actual air sacs that do the actual absorption. So absorbing oxygen in and taking CO2 out is affected in someone with emphysema. Remember that this goes two ways. Anytime that oxygen is entering a tissue, CO2 is also exiting. Someone who has a problem with their alveoli, whether they have emphysema or not, because I'm about to mention one of the new questions that doesn't say anything about emphysema but asks about alveoli problems. Someone who has a problem with the alveoli will have two major problems. They will have decreased oxygen absorption. And the way I'm going to write that is they're going to have decreased absorption of incoming oxygen. That's what everybody thinks of. This is where most people stop. What happens if you have emphysema? You get less oxygen. That's where most people stop. There's a whole nother side to that that is equally problematic and actually more readily noticed by your body, which is decreased absorption, same thing. So alveoli are all about absorption. Remember that absorption is when something makes it into or out of the bloodstream. So you can breathe all you want, but if your alveoli are not adequately absorbing that oxygen into your bloodstream, you're going to be low on oxygen. You can breathe out all you want. If the CO2 is not attaching properly to the alveoli so that it can leave, again, you're going to have the same problem. So decreased absorption of outgoing CO2 would cause a buildup of CO2. So when you think about a problem with alveoli, you need to think about both sides. It is equally bad, if not worse, to have CO2 unable to exit the body as it is to have O2 having trouble getting in. I'm not actually enough of a physiology expert that I could tell you if one of them is more harmful than the other. If I were to guess, I would say CO2 pileup is slightly more harmful than a lack of oxygen. They're both bad. So when you think about someone with emphysema and you think about the effect, if at all possible, if there is an answer choice that is encompassing both sides of the problem, that's what you want, is the one that encompasses both sides of the problem. There's a new question that's real specific, that's just more specific with the same thing. Basically says if there's a problem with the alveoli, if the alveoli are not functioning, what is the result? I've seen a lot of people mention this new question to me, and for whatever reason, the thought processes that I'm seeing behind it are not going in this direction. So people are not connecting the emphysema thing to the alveoli thing. Here's what's really important. Whenever they ask you, because there are multiple types of questions in multiple places that say, what happens when this stops functioning? What happens when acetylcholinesterase enzyme is suddenly absent at the neuromuscular junction? What happens when the alveoli suddenly stop functioning entirely? You always need to go to the very, 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 very specific spot that's broken and think about what that thing is supposed to do. Don't think big picture. Don't think what happens 5 steps after the alveoli. You want to be picturing, what do the alveoli themselves, removing every other part of the breathing equation, what do they do? The alveoli do absorption. What is absorption? It's putting oxygen into the blood. Very, very important, because that's essentially the answer. What happens when the alveoli stop functioning? Oxygen doesn't make it into the bloodstream. We don't absorb oxygen into the blood. The other answers that they have there, very characteristic of this type of question, is like your heart won't be able to beat and put out the full amount of blood. Well, that could eventually happen, but that's not the direct result of the alveoli. So you want to be looking microscopically at the first, most immediate thing that's going to happen that is most directly the result of this particular thing not functioning. The alveoli not functioning really will only cause one direct result, and that's going to be oxygen's not absorbing into the blood. CO2 is not going to be able to leave. So if the alveoli can't pull the CO2 from the blood, then the CO2 can't get out of the blood. So what happens if an alveoli breaks? You can't get oxygen into the blood. You can't get CO2 out of the blood. That's as far as your answer goes. Don't think about the next thing that happens because of that happening. Think about that. This is what they want. They don't care what happens after that and after that and after that. They care about this. Same thing on any question like that. So without me going into any other examples, if they ask you what happens when something breaks or disappears or a particular disease is active that you know reduces the activity of something in particular because you've studied it, that's what they want. You want to think about exactly what the function of that little tiny part of the process is and what happens when it's gone. 2 more systems. I'm going to try to make these 2 as quick as I can because there are definitely there has been a reduction in questions out of these systems, and these are the systems people are doing really well at. Cardiovascular has a few components. I'm mostly going to focus on reviewing what those components are and essentially giving you the right setup to keep studying cardiovascular on your own. Just like with anything, key function of the system. We've been talking about the key function of cardiovascular all day, so I'm not worried about that. But it is essentially the transport system. So both the blood and the bloodstream, so the blood vessels, and the heart are the 3 parts of the cardiovascular system. You have blood, you have the vessels that carry it, and you have the heart. All of that has one sole purpose, and that is transport. It transports oxygen into all the tissues to do the cell respiration cycle. It transports CO2 out that's a byproduct of that same cycle. It transports urea and ammonia and uric acid and creatinine to the kidneys so that they can leave. It transports calcium from the bone into the bloodstream or vice versa. It is a transport system. Anything that is circulated or delivered to any place in the body, that's who's going to do it. Remember that there's always 2 sides to it. You need to know the parts of blood, in particular, the globulins and hemoglobin. What is the function of that? And then fibrinogen as being involved in clotting. Those are detailed questions. So if you get those questions, just knowing what they are, what their function is, that's it. It's not a complicated question. What happens if fibrinogen disappears? It's just what is the essential function of fibrinogen? Blood clotting. All of this is important, but all of this is probably stuff you have down. So hemoglobin is who actually carries oxygen and carbon dioxide. Always put oxygen and CO2 hand in hand. They do exactly the same thing. They're just opposite ends of the arc. And then red blood cells are erythrocytes, so they transport oxygen, CO2, nutrients, and lots of other things. White blood cells are the next system we're talking about. Those are immune and lymphatic. Know the difference between the atria and the ventricles, generally speaking, and then a little bit more specifically. The atria are the top chambers. They're much smaller. They're much less muscular, and they serve to slow down and organize the blood rather than being pumps. The ventricles are large muscular pumps. They sit below the atria or inferior to the atria. The left ventricle pumps the blood out to the body. The right ventricle pumps the blood to the lungs. The right ventricle is the most muscular chamber. I added that because HESI has a very specific question about that. I think the CAP might have that too. The right ventricle, why do I have right ventricle there? I'm sorry, that should say left. Hopefully I will have fixed that by the time you see these. I'm going to try to go back and find all my errors. The left ventricle is the one that pumps the blood to the body. That is the most muscular. So cross out right if it is still there. Hopefully I found it and fixed it by the time you're looking at this. The left ventricle. That's very logical because the right ventricle just has to go to the lungs. It doesn't require a huge muscular intensity to get from the heart to the lungs. They're right next to each other. What requires a huge intensity is to get all the way up to the top of the brain and all the way down to the toes. That is a major, major travel distance. The way that your blood can make it all the way out like that is a huge muscular contraction in the first place with the ventricle, the left ventricle. And then the smooth muscle that lines the arteries helps to continue propelling the blood as it's reaching different points in the arterial tree. Know that heart activity is caused by pacemaker cells. So you have an SA node and an AV node. You don't need to know exact on where those are and what each one does, but you do need to know that independent of the nervous system, The heart makes its own electricity. So the heart generates its own impulse, and it is not dependent on any other system. That is the part that you need to know. The nervous system certainly does affect the heart. It can speed up the heart, slow down the heart, increase the blood pressure, decrease the blood pressure, all that good stuff. But the actual heartbeat existing in the first place has nothing to do with any other system. The SA node does that all by itself. Know what the blood flow is. Know the pulmonary circuit versus the systemic circuit. That's all listed carefully here, and we went into great detail. What I'm going to focus on is what is the function of each circuit. You always need to be able to describe in a sentence what something is trying to do to be able to memorize its details or its steps. I've tried really hard to emphasize that all throughout this review. So let's do that with the circuits. What does the pulmonary circuit do? What is its job? Why is it there? How does it differ from systemic? That is the key to you being able to say, here's the components that are part of each. Pulmonary carries blood to the lungs, which of course is where the alveoli do gas exchange. We get rid of CO2 so that it's out. We get new oxygen in. The whole function of the heart in the first place is to deliver oxygen to the whole entire body and take back CO2 from the whole entire body. So the pulmonary circuit is the interaction between the heart and the lungs, where we exchange so that we can bring more oxygen out and take more CO2 away. So what does the pulmonary circuit do? It carries blood to the lungs. It does gas exchange, and it returns it to the heart, and now carrying oxygen. The right side of the heart is who's involved in that. So the right side is pulmonary. The left side is systemic. So when blood comes back from the body, it comes into the right body. It comes into the right side of the heart. It gets organized by the right atrium. The right ventricle sends it over here to the lungs. It does what it needs to do in the lungs. The lungs send it back through the pulmonary vein. That is the last step that is in the pulmonary circuit. So the pulmonary circuit is the blood entering the right atrium, going through the tricuspid valve, going into the right ventricle. The right ventricle propels it to the lungs. The lungs do what they're supposed to do, and they send it back. And that's when the systemic circuit takes over. Systemic circuit is supplying oxygen to all the tissues, all the organs, all the systems, and picking up their CO2 in order to return that to the heart. So that's going to begin the second that the blood returns from the lungs. So there's a very distinct line between the systems. As soon as the blood comes back from the lungs, it's coming into the left atrium, and it immediately starts the systemic circuit, goes through the bicuspid valve, enters the left ventricle. The left ventricle has a huge contraction, sends the blood out to the body via the aorta and all the arteries that follow. Blood travels through all the blood vessels to the tissues of the body. It picks up the CO2, it returns that using the veins, and it enters the heart. So you can study this however it makes the most sense with the way you think. The way that I studied it is I got all the steps down from the very, very beginning when the blood enters the heart, all the way to the very, very end when it enters the heart again. Then I broke them into circuits. Because the circuits don't necessarily exactly go in the order that you might think of the heart. That said, you can start right here at step 1 of pulmonary, and you can go through right here, which is the last step of systemic, and have an ordered process with a very clear line between one circuit and the other. The coronary circuit, remember, is one more circuit. It's active as part of systemic, but they could specify it and they could ask you specifically, what does the coronary circuit do, or when is it active? So right after the left ventricle contracts to send blood out to the body, one place in the body that is going to get blood is the coronary artery, which is actually serving the heart. So what does the coronary circuit do? It serves the heart with oxygen. Remember the analogy I made in class is to say the heart doesn't need its own supply of oxygen because it has blood running through it all the time would be like saying you don't need to eat if you work in a restaurant because you're around the food all the time. The heart, just like every other organ in the body, needs a specific artery delivering specific oxygen to it. Know that arteries transport blood away and have active pressure. Smooth muscle. Know that veins deliver it back. So obviously, you want to think of the arteries as being whatever's moving out of the heart, the veins as whatever's moving back. There is a very specific reason that I don't have oxygenated and deoxygenated labeled there. And that is that in the systemic circuit, arteries are always carrying oxygen, veins are always carrying CO2. However, in the pulmonary circuit, it's the opposite. And you can ground that in pure logic, because if the blood is leaving the body, but it's leaving the heart, sorry, if the blood is leaving the heart, but it's not going to the body, it's going to the lungs, that's deoxygenated blood, but it is going away from the heart. In other words, there is one artery in the body that carries deoxygenated blood, and there is one vein in the body, which is the pulmonary vein, which carries oxygenated. So I just recommend not studying it that way. Don't remember it that way. Just remember transporting away and bringing back, because that will tell you whether something has oxygen or not based on where it's leaving to go to or where it's returning from. Know that this is the blood vessel hierarchy. So beginning with the largest artery, the aorta, then the large arteries like the carotid, then the regular arteries, then the arterioles. The arterioles are entering organs or tissue areas. So you might add that now that you've studied this some. Capillaries are the actual exchange site. So O2 versus CO2 exchange there. Venules are exiting an organ. So just like entering and exiting somebody's driveway, you don't pull right onto a highway, you pull onto a little street and then a little bit bigger street and then a little bit bigger. Your blood veins and arteries do the same thing. So as you're approaching an organ, you're getting into a much smaller and slowed down version of the vessel. As you're exiting the organ, you're still being very careful. Then you're going to go into a bigger and a bigger flow so that you can get back as quickly as possible. Remember that systole is the contraction of the heart muscles. It's the top number in the blood pressure. Diastole is the relaxation of the heart muscles. It is the bottom number. Know how to kind of describe blood pressure. So the maximum amount of possible pressure that could be measured in an artery is the systole of that artery. And then the minimum possible that can be measured in the same artery is the relaxation. So blood pressure is taken to determine what is the highest pressure that exists in that artery, what is the lowest pressure that exists in that artery. You really don't need to worry about issues of the circulatory system. There's really not anything active about that. If you're doing HESI, just a reminder, you need to know the blood types, just very generally, what is the antibody and the antigen that each blood type has? Is it universal in any way or is it not? And then the little bit of embryonic development stuff that I have listed here, this is pure memorization if you are doing HESI, only if you're doing HESI. I put a little line and made sure it's labeled HESI. If you're doing TEAS, there is literally no use for that information. The last system is the immune system. I'm going to make this one very fast because I think this video is approaching at least 5 hours total. So immune system is actually very simple. Hopefully you really got down your first, second, and third line. Again, I'm not going to go into super detail about the lines because I'm sure that most of you have that down by now. If you cannot recite the function and the components of the first line, the second line, the third line, you would want to go back to the end of Anatomy 4. Signs of infection. So how can you tell someone has an infection? They have a fever, which is a heightening of the body temperature to try to fight pathogens by making them too hot and uncomfortable. fatigue because the immune system is taking all your energy, and increased white blood cell count. This is a common question. What would you see in someone with an infection? You would see an increase in their white blood cell count. Why? Because white blood cells attack pathogens. So you're going to have more of them. You're going to see that. There is no effect on red blood cells at all from being sick. First and second line are general. They're like little blind cells that have no clue exactly who or what they're taking on. They just take on anything that seems like it's not exactly supposed to be there. And there's different mechanisms that they use to attack it. First line of defense is not cellular. It's purely physical. It's mechanical. So it's like the skin is there to just prevent most pathogens from getting in the first place. The mucous membranes release mucus so that they can capture and remove the pathogens in the lungs. The gastric secretions refers to the acidity that is present in the digestive system to basically increase the odds exponentially that a pathogen just dies when it comes through there. Second line of defense is like actual white blood cells. Most of them are macrophages or phagocytes that come and engulf and destroy a cell by doing that. But again, they don't exactly know what they are attacking. When we get to the third line, that's the only line of the immune system that actually does know what it's attacking, and it knows very specifically what it's attacking to where it has built a specific defense against it. Knowing those lines is very important. Most common immune system question by far has to do with cytokines. They will say one of two possible things. They will say that they are chemical messengers, or they could say that they are cells, it doesn't matter, that activate other immune cells. So whenever you see that they activate other immune cells, most likely the answer is cytokine. The other possibility is the T cells, but they're never going to put both of those answers there at the same time. So if you see something about activating other immune cells, it is either cytokines or it is T cells. If you see something about squeezing through capillary slits, that is absolutely 100% cytokines. Again, ground this in logic. A cytokine is a chemical messenger that is supposed to essentially go to the site, scope it out, see what's going on, see what kind of resources might be needed. So it's kind of like the scout, and then pull the resources in. So activate the other cells, help them get to the site, help them get started when they get to the site. That is essentially the role of a scout. So it goes, it scopes it out, it sees what's going on, how much of a problem it is, decides who needs to be mobilized and activated, and then commands those things to come out and helps them do what they need to do when they get there. T cells activate in a different way. T cells activate a third line of defense. So a third line response is where we know who we're attacking. We have attacked them before, and we're going to use a memory function to attack them. Cytokines activate the second line. So when a cytokine goes out and it scopes out what's going on, it doesn't actually identify a specific pathogen because it is not the type of cell that can do that. That's basically it off of this page. The only other thing is knowing that natural killer or NK cells and interferons play a role specifically in cancer and occasionally in viruses. If they were to mention those, it will be super simple because most people have no clue what an NK cell or an interferon is. Interferons prevent viral replication by messing with protein codes. Natural killer cells basically produce a little hole so that they can rupture the protein. Just knowing that those two are specific to virus and cancer and kind of everything else is specific to bacteria is all that you need to know there. You just need to understand HIV/AIDS. I did an explanation of this and it's fairly well written out here to where I'm not going to go back through that. I do repeat multiple sclerosis here, but it's also talked about in a couple of other classes. And that leaves you with the types of immunity, which are super important. I will tell you, you need to know all of these, but artificial and natural passive immunity are the two that get asked absolutely the most. Right now, right at the moment. There are active immunity questions, so you do need to know all of them. And a reminder of how I told you to study this. Again, any of these systems that you are still struggling with understanding or remembering, it's not going to be enough to just hear this review. This review is just supposed to get you thinking again, get you back in your notes. But if there are things you actually completely don't remember to where I can't jog your memory with a simple comment, or things you didn't actually fully understand, you need to go back to your original lectures for that. When I did this in class, what I told you is active and passive immunity has to do with who makes the antibody. Remember that when I say the word immunity, I mean you are immune to something. I mean that there is a third line defense that has been made. To say you're immune to something doesn't just mean your immune system can attack it. It means your immune system knows what it is and has a programmed defense for it. So all of these contain the word immunity. All of these mean that your body is literally immune to whatever it is, and it can kill it and attack it and rid your body of it so fast you will not know it came through. So who makes the antibody is the difference between active and passive. Active is you make the antibody within your own immune system. Your B cells create the antibody. Passive is the antibodies are put into your body. They're already in the form of an antibody, and your body doesn't actually make them at all. Natural and artificial is semi-obvious what those are. Natural comes from natural means. You bump into a pathogen, you bump into an antibody. Breastfeeding is a way that you can bump into an antibody, and it's totally natural. Artificial is some sort of scientific construction, modification, introduction, alteration, something. So natural, active, you're always going to have a combo of one of these and one of these. Natural active is totally the normal way of making an antibody. You bump into a pathogen by mistake. It tries to infect you, or it does infect you. Your body makes a defense for the next time that it sees that, and you are now immune. Chickenpox is a great example. If you get around someone that has chickenpox, you're probably going to get it if you've never had it before, but you can't get it again many years later when your child gets chickenpox because you are immune from natural active immunity. You came in contact, you got sick, your body used the fact that you got sick to memorize, understand, and create defense, and you won't get sick with it again. Artificial active, you are still, so active, you always want to kind of go back up here when you're first running through these and studying these so that you can make sure you're really grounding your terminology. That way you don't memorize it. Don't memorize what artificial active is. Know what artificial is, know what active is, know that they come from two different spots. And then on the spot, when you see the term, define it based on what the words are that are involved. So artificial is going to mean that there is some type of scientific messing with it. And then active is going to mean you make the antibody within your own immune system. So the antibody is made in the normal, traditional way. Well, where do we combine scientific modification with you making an antibody? That would be a vaccination. So they are introducing an antigen, a pathogen, to your body, but it's modified in some way to where it doesn't make you sick like it would if you just came across someone who had the flu, but it still makes your immune system think it's there, and your immune system still makes antibodies. So there's two ways that you can actively make an antibody and then be immune to something. You can either come in contact with the disease or the pathogen naturally and make an antibody, or you can intentionally come in contact with a modified version of the antigen or pathogen and make an antibody. Those are the two that are active. The passive means that an antibody is placed in your body. So instead of your B cells making an antibody, you just get an antibody. So the work is already done. The antibodies are put into your bloodstream. And if that pathogen comes along, you can kill it without having made any effort to create a defense. Natural passive is breastfeeding. I see this question on the T's a ton all the time. antibodies are made by mom's immune system and given to baby. So a lot of the antibodies that you have came from your mom's body doing one of these two processes here to form actual antibodies. So it's passive because you didn't have to make the antibody, your mom made it. And then artificial passive is artificial and passive. So not only are we scientifically messing with something, we are scientifically messing with something to put antibodies into your bloodstream. There's only one really good example of that, and that would be like anti-venom for a snake bite. So that would be a situation where, yes, your immune system is capable of mounting a defense against poison, but you would be very likely to be dead by the time that defense was mounted, because the third line of defense is for the next time that this pathogen tries to come along, not for this time. So you have to completely fight out an infection with your second line immune system and then have it come back later to actually use your immunity. In the case of a snake bite, unless it was super minor or you were super vigilant at keeping it away from the rest of the bloodstream somehow, you would be dead before the antibodies were made. So they do have a process where they extract antibodies from something that has been bitten, and then they use those antibodies, they put them in your bloodstream, and instead of your immune system fighting the venom from the snake bite, the antibodies just destroy the venom within your bloodstream. Here's the third line of defense. We've talked a fair amount about the third line of defense as part of everything else, but remember that that is the one that makes antibodies. It is the one that is making a defense for next time. So it has to be active alongside the first and second line of defense. Basically, with the third line of defense, you want to remember that these are programmed responses. There's a response for each antigen, which there are millions and millions of. And the only way you're going to have third line immunity to something is if you have been exposed to it somehow before. Remember that helper T cells are the ones that kind of get and bring the information in, but B cells produce the antibodies. I always remember that because B cell antibody. So B cells make antibodies and then hold them until that infection tries to come back. Lymphatic system. So just make sure that you are familiar for lymphatic with what the spleen is. That's where red blood cells are stored, filtered. Decisions are made about how many red blood cells need to be gotten rid of because they're too old versus how many can be kept and circulated again, and then storage of extra red blood cells. Ones that are old, that are no longer functional, get degraded by the spleen. Some of the blood that's very good, that's young, that's healthy, is just stored there so that there's extra blood. And injury or damage to the spleen can be really critical because it is holding a lot of your blood. That said, nowadays we have a lot of very quick ways of fixing a rupture to the spleen that we didn't have before. Know what the thymus is. Know that T cells are called T cells because they're made in the thymus. Every other immune cell, everything but T cells, is made in yellow bone marrow, but matures in the thymus. So you have yellow bone marrow in all of your long bones. That's where your white blood cells are being made. Then they're transported by your lymphatic system to the thymus, which is in the chest. That was the one that's in the endocrine stuff that you're not doing anything with when you're in that unit. And that's where everything matures. All the lymphocytes, all the white blood cells mature there. But T cells are both made and matured in the thymus. So know about yellow bone marrow versus red. Red bone marrow makes red blood cells, simple as that. Yellow bone marrow makes the white blood cells, but not the T cells. And then know about the spleen and have a general idea of the function of the lymphatic system, which is this part down here. It's essentially a network just like the cardiovascular system, except it only carries around lymphatic fluid for the immune system. One other totally weird and random thing that I guess I'll put up here toward the beginning of this. There is a question that essentially says something like, if a pathogen gets past the skin. So remember that part of the first line of defense is the skin. The skin is probably the number one thing that protects us from infection. Because if I want to get into somebody's digestive system, I can't just enter anywhere. I have to get to their mouth. That's the only way to access the digestive system. That's because of skin. If it weren't for skin, there would be a million ways to get where you wanted to go. If a pathogen gets through the skin, and you have to read into the question because it actually says the pathogen quite literally breached the skin. It made it through. It's all the way through the skin. And then it basically says, now, who is responsible? And this is a weird question because it's combining the skin and the other systems in a weird way. So it's worth mentioning. If a pathogen got all the way through the skin, that means that the skin has failed. That means that the first line of defense in that instance has failed. So who is responsible for it now? The immune system. The skin, although an important component of the immune system, is its own system. So we don't consider the skin's presence to be the immune system. We consider it to help the immune system. Once something actually makes it through the skin, that basically means that it's made it to the bloodstream. If it makes it through into the bloodstream, who is responsible for it is who we can mobilize in the bloodstream, which is the immune system. So your skin and your immune system both work to try to keep the pathogens away. But if your skin completely fails, which is essentially what this example question does say, then your immune system has to take over. And by immune system, I mean your second line immune system with cellular defense. They don't ever specify that. It literally is just like, what system is responsible once the skin fails? It's the immune system. More specifically, it would be a cellular, like macrophage phagocyte type response. So hopefully this didn't get too super crazy long, but that is it for intense review. Again, remember, I did not go through everything. I did the very best I could with lots of advanced planning to try to get to everything that's super crucial or that might have been easy to forget. But anything that we hit here or anything you see in the notes that we didn't hit, go back to your other lectures. You need both. You need all 5 of these lectures. And if you've done the other anatomy review, that's also helpful. Because if I mention it in lecture, if I mentioned it in the original class, it is important. And this would be an 8-hour long, actually like a 10-hour long video if I mentioned everything again, because it would be a repeat of everything from the other classes. So this is my best effort at pointing out some of the newer material and connecting some of the stuff back to what you did before. Any big concept you're struggling with, confused about, concerned about, any of the above, you need to go back to your original lecture. Once you've done that, if you're still having particular issue or questions in some area, then you can let me know so that I can help you advance past it. That is it for Anatomy Intense Review. I will see you guys later.